All right, so I'm a postdoctoral researcher in Frank's research group. We are working on probabilistic programming and applications in science, including high-energy physics and high-performance computing. I'm mostly interested in automatic differentiation, which will be the subject of this talk, and evolutionary algorithms and a bit of computational physics. So deep learning is one of the themes in this summer school, so I thought it would be good to provide an overview of that before going into the automatic differentiation part. So I don't know your level of familiarity with it, but let me just cover basic concepts in deep learning. So it is a reincarnation of artificial neural networks, which is a very old idea dating back to 1940s and 50s. Here you see Frank Rosenblatt, the inventor of the perceptron, which was, by the way, a machine instead of an algorithm, holding a set of neural network weights, which were like potentiometers that you can adjust by turning them and trying to teach the network to some task. And we use backpropagation, which was invented in the 1970s. So all these things are very established old techniques that are currently working very well due to the things I'm going to summarize. So it is currently the state of the art in computer vision. This has been the case since this ImageNet competition in 2012, when someone attempted to apply convolutional neural nets for image recognition, and which was almost revolutionary. It halved the error that was achieved by non-deep learning techniques previously. You can see it happening here. This is basically the point where deep learning got to have the fame it has today, and it replaced hand-engineered features. And modern deep learning systems surpass human performance for image recognition tasks. This is also the case with speech recognition. Previously, people were using statistical methods based on hidden Markov models and Gaussian mixture models. Again, deep learning systems starting around 2012, they applied neural networks trained with lots of data, and they surpassed the previous state of the art. Another interesting application is machine translation. This is based on recurrent neural networks or convolutional neural networks. So again, this replaced the previous hand engineering features based statistical translation pipeline, and all major companies are deploying this as their daily machine translation system. The last was Facebook, which replaced their machine translation system just this month, a few weeks ago, with the full deep learning system. An interesting thing to see here is this plot for Google's neural machine translator. Here you see with blue the previous machine learning approach, non-deep learning. Yellow is the human. So you can see, for example, for the language pair, like translation from French to English, you get near human level translation performance, the quality of translation. And this is all happening just by supplying data to recurrent neural network. So I will try to cover why these things are starting to work so well, what makes deep learning tick, what is really the thing behind it. So probably all of you are familiar with artificial neural networks or the idea. So you have a mathematical structure very loosely based on a real neural cell. So you have a collection of inputs weighted by some connection weights. You have a summation, and you have a nonlinear transformation. And this goes on into the other nodes in your network. And you have like a selection of activation functions. This is the nonlinearity. The fashion right now is to use rectified linear units and hyperbolic tangent. There's research going on about the properties and why they work so well or why they don't work for different applications. So you have basically three types. These are the classical types. You have feed-forward neural nets, you have convolutional neural nets, and you have recurrent units. Basically, you build models as combinations of compositions of these three basic building blocks. Lately, because the field is so active right now, there is research going on in introducing new building blocks, and the focus has been on introducing neural network blocks that emulate algorithmic control. For example, you have something called the neural Turing machine, which is a differentiable Turing machine implemented as a neural network. You can train it with gradient descent to do algorithmic tasks such as copy and sort, and you can inspect the behavior of the neural net where you see Turing machine-like behavior. There are other techniques inspired by that, like discrete interfaces or stack augmented neural networks. So the important thing to emphasize here is that these neural networks don't require any feature engineering. You don't have to think about what is the feature I need from my data to make this problem solvable. You just work with raw data. That's a very interesting thing over previous state of the art. So for example, if you are doing image recognition, your input is the raw pixels and your output is the object labels. So you can have literally the RGB pixels going in one end. You can have like a person's name coming out of the other end. Or in speech recognition, you would just put the raw waveform. And what is happening here is in these many layers, you learn a distributed representation. And this is also called representation learning. So another important thing to emphasize is the reason behind the name deep learning. It has been shown consistently that deeper architectures are better than shallow architectures. Deeper meaning you have more and more layers for a task. You can see the trend, like this is the first neural network in 2012 for winning image recognition task I mentioned. It only had 8 layers, then you go up to 19 layers in Oxford VGGNet, just 2 years after that. And just 2 years ago, the winner of the same competition was this neural net with 152 layers. And people are inventing tricks to have more and more layers work with gradient descent. That's basically the trend. Another important thing in deep learning is data. This is also one of the reasons these neural network architectures were not performing very well back in the 1980s and 90s. They didn't have enough data. Now big companies have these, and this is the reason actually these companies are big players in deep learning, because they have access to data, they have access to computational resources. The thing with deep neural architectures is that you need millions and millions of labeled data if you are doing supervised learning. This is something Frank was also talking about. This is a quote from the deep learning book, the textbook of the field. It says you need at least 10 million labeled examples to be anywhere near human performance for any task. So this is one of the biggest limitations, and this is the reason probabilistic programming and deep learning combine very well, because basically what we are doing is we are supplying the data coming from a probabilistic model and using that for training neural nets. Another thing that enabled the deep learning revolution is the hardware advances and graphics processing units. The main reason behind this is, like, at the end of the day, a neural network is just a series of matrix multiplications, and these are implemented very fast on GPUs. And this basically starts around 2007 and quickly became the standard thing to do. If you are doing deep learning, you are running matrix multiplications on a specialized hardware architecture. And there are things like people are designing hardware specific for deep learning applications. This is also a current trend. This one is sometimes omitted. I personally think this is a very important thing in the deep learning because you have access to these machine learning frameworks that allow you to express models in a very straightforward way. This wasn't the case, for example, in 1990s. The training a neural network was treated as a black art. Like you were supposed to implement everything from scratch, including the lower level implementations. So now, for example, today, if you start doing deep learning, you just pick your favorite deep learning framework. You would be good to go in a couple of hours after reading some tutorials. So you can run other people's models, you can start training. And today, in the later part of this talk, I'm going to talk to you about PyTorch due to some advantages it has. And all these come with high performance backends. Like if you have a CPU-based system, you have MKL. If you have GPUs, you use CUDA. So these things are just out of the box good to go. And very important bit is learning. How do we perform learning? Is basically we do backpropagation to compute the gradient of a loss value for a task-specific loss with respect to the learnable parameters of your neural network. And we do stochastic gradient descent, or we use in practice adaptive learning rate algorithms such as Edelman or RMSProp. For these, we need derivatives, and I'm going to talk to you about how these derivatives are computed. So to sum up, these are the three most important elements. You have neural networks, you have data, and you have gradient-based optimization. And for gradient-based optimization, we need derivatives. So the rest of the talk is about how we get these derivatives. So I'm going to cover three cases. You can do manual or symbolic differentiation, you can do numerical differentiation, or you can do this thing called automatic differentiation. The manual one is the one you know from your calculus course. You have rules of differentiation, such as the addition rule, the multiplication rule. It's just a rule-based mechanistic procedure that you can apply until you get all the derivative. This interestingly, when Leibniz introduced calculus, he has a quote in his book saying that one day this can be done by a machine. That's an interesting thing. That was a reference to this being a mechanistic procedure. So you can do this. And you need to do this if you are doing analytic solutions, if you are doing proofs, if you are doing analysis of stability. It's good to have derivatives written in front of you. But they are unnecessary if you are just interested in numerical derivatives for the purpose of gradient-based optimization. And this was, until very recently, an interesting thing in the machine learning field was that, for example, this is a real paper. If you zoom in enough, you will see which paper it is. I just picked this one for making this point. People used to do, like, you introduce a new machine learning model in the first 2 pages. Then you spend all these pages for deriving the gradient equation so that you can use it in an optimization procedure. This was before these machine learning frameworks and the ability of getting derivatives for free. So this is, thanks to automatic differentiation, this has changed. So you can do you can automate manual differentiation, like the application of manual differentiation rules. You can use symbolic algebra packages like Mathematica to do this task for you in a error-free way. The main issue here is that when you differentiate an expression, you have a problem called expression swell. And this is a very important limitation. You get exponentially more complicated expressions as a result of differentiation operations. Here I attempted to plot how expressions swell can be seen in a logistic map. So for example, if you have this logistic map equation, and if you have the number of times this map is applied, As n increases, you see like this is the original logistic map equation, and this is the number of terms in its derivative. So this is a very important thing you should think about. And if you are doing, if you are, for example, familiar with Theano, the machine learning library, which uses symbolic differentiation, it has a step specifically implemented for taking care of this expression swell problem. First, you differentiate, then you simplify these terms into something more manageable. Another problem with these symbolic derivatives is that they are only applicable to closed form expressions. What I mean by that is like you can differentiate something that looks like this because this corresponds to a mathematical formula. You need to be able to write it down in terms of maths to apply differentiation rules, but you cannot have the derivative of something with algorithmic control flow. This is an important limitation that TN and TensorFlow is facing. For example, you are not free to implement your algorithm in a free way. You are supposed to use the limited symbolic graph mini language to express control flow operations. So I will talk a bit more about that. You can do numerical differentiation. This means you are approximating the values of derivatives by using the limit definition of derivative with a small constant. This is very straightforward and easy to think about, but the problem with it is that you get approximation errors, you get round-off errors, and you get truncation errors. You might think that by decreasing h as much as you can get rid of the errors, but this is not the case, unfortunately. Up to some point, let's start from here, you can decrease your truncation error by decreasing h, but if you keep decreasing it, then you have something called the round-off error. This time it becomes dominant and it destroys all your derivatives in a big system. So this is not applicable to any system more complicated than the small model. You can improve the situation by using better approximations, but none of them really take care of the problem. And another problem with this is for computing a gradient with something like this, you have to evaluate this sort of formula for as many times as your number of input variables. For example, if you have a function, like scalar function of n inputs, you will have to compute the function forward n times for computing the full gradient with numerical approximations. So that's also out of the question, and we come to the subject of automatic differentiation. So this is a small but established field in scientific computing. It's used in things like computational fluid dynamics. There is active research going on, and this is connected with machine learning through the backpropagation algorithm. So if you heard about backprop or used it, you already know a bit of this. It corresponds to the thing called reverse mode automatic differentiation. So what I've been working on is to bring techniques from this field into machine learning so that you can do more intelligent things than backprop. So I will briefly cover how automatic differentiation works. It also gives you an understanding of how backpropagation works if you are interested in knowing about it. So in automatic differentiation, you have an algorithm. Let's go there, or let's look at this thing. Like it's a function of two variables. So you have techniques of taking this computer program and giving you another program that evaluates this function, and in addition to that, it evaluates the derivative of the function. And this can be completely automated. So, for example, what you see here is the forward mode automatic differentiation. I will cover it in the next slide better. But you see that because you have a multiplication, C is a multiplication of A and B, you still maintain that here. C is a multiplication of A and B. And this derivative of C is this expression coming from the multiplication rule from the rules of differentiation. So you apply that to all your elementary operations in your trace, and you get the derivative with respect to one of your inputs in the end. So I will expect y is that one of the inputs in the next slide. And an important thing to point out is that you get exact derivatives. This is not a numerical approximation. It's as good as it gets. It's as if you had like a symbolic formula for your derivative and you evaluated it, and so it's not an approximation. So automatic differentiation has two modes. These are called forward and reverse. Forward is very straightforward, and reverse is the one that people know as backprop. It is a bit difficult or strange to understand the first time you see it, but it's not really so bad. So let's start with the forward mode. Let's say you have a function that looks like this. You can express this as a computation graph with two inputs here and the output here. And these are intermediate values that show you the dependency structure of this function. So you can see that you do multiplication here, you do subtraction here, you do, I think this is a sign, and you combine everything to get your scalar value. So in forward mode, you start by selecting a variable of differentiation, any of your inputs. Then you mirror your computation graph and introduce for each intermediate variable a new variable called the tangent variable. I think I should, okay, it should have set tangent here. This is called the tangent. And this means the derivative of that node with respect to the input node you selected. So in forward mode, you take the derivative with respect to one of your inputs. This is the difference between the forward mode and the reverse mode. So let's say we want to differentiate this function with respect to the first input, x1. So here on the left, you see the regular execution of the function. You just so I selected 2 and 5 as the input values, and when you execute the thing, you get 11.65 as the output. This is called the forward evaluation trace. And in addition to this, you do a derivative trace, and you set the derivative of x1 to 1 and the derivative of x2 to 0. This has the meaning that you are taking derivatives with respect to x1, because x1's derivative with respect to itself will be 1, and because these are considered independent inputs, this thing will be 0. And if you do this, and if you just derive the differentiation rules corresponding to each elementary operation in your execution, and you keep using the values you get, and in the end you get a value here which corresponds to the derivative of your final scalar with respect to the input value for which you set the tangent to 1. This is the forward mode. And in the reverse mode, we will do the reverse thing. And you will see why it's used so much in neural networks and backpropagation. So what is happening in okay, let's just skip this. What is happening in the reverse mode is that as we introduce these tangents in the forward mode, now we introduce nodes called adjoints. This is just a terminology they use in automatic differentiation field that hold derivative values. But there's a little point to be careful about. So these new nodes, they represent the derivative of the final output with respect to that node. If you remember in the forward mode, this thing was the derivative of that node with respect to an input. In this case, this derivative represents the derivative of the output with respect to this node. And you do things in reverse. So let me try to explain that. The thing on the left, like this column, remains the same. It's just the forward evaluation of the same function with the same values and the same output. So corresponding to each row, each elementary operation, again, you have the differentiation rules. But this time, we don't set anything in the adjoint trace starting from the top, because we start from the bottom. So let me say this again in a clearer way. So you do the forward evaluation. You are here, or you start from left to the right. You compute all these nodes. Then you do a back propagation. which I represent with this arrow going back towards the inputs here. And this time you start by setting the adjoint of the output to 1. Again, you can interpret that as being 1 because this is the derivative of something with respect to itself. And you go through these operations in reverse. And at each point, you get the derivative of the node you are in, derivative of the output with respect to the node you are in. So if you keep propagating things backwards, you get the derivative of the output with respect to both inputs in one reverse evaluation. As you can see, like if you have millions and millions of these inputs, it will still take you just one forward and one reverse evaluation to get the full gradient, the derivative of your one output with respect to all these inputs. So this is the reason this is used so much in deep learning, because we have a case where we have a loss function, a scalar value, and we take gradients of that with respect to millions of neural network weights, for example. And this is the reason backpropagation was invented in neural network community. So this is how something like this looks like in a machine learning framework, PyTorch. We will see this in the afternoon exercise session. And to sum up, in the extreme case where you have a vector valid function of one variable with forward AD, just forward run, you can get the full set of partial derivatives with respect to the one input in just one forward evaluation. And in the other extreme, if you have a scalar valid function of many inputs with reverse AD, you can get the full gradient in just one application. And there are things in between. This is not appreciated in the deep learning community right now. In the general case, if you have a function with n inputs and m outputs, backpropagation is not always the thing to do if you are after efficiency. Backpropagation is only better if you have significantly more inputs than your outputs. In the other case, you would prefer forward differentiation, but this is not encountered so much in machine learning field. So I will connect all this to what is going on in deep learning frameworks. So you can classify deep learning frameworks into two types. The first I call symbolic graph builders, and the second is the dynamic graph builders. This name is emerging in deep learning to refer to automatic differentiation. So in symbolic builders like TensorFlow or Theano, you implement your models using symbolic placeholders, using a mini language that is given to you by the framework. For example, this here is in Theano. You have like a input tensor. You do shuffling. You do element-wise multiplication. You are supposed to implement all your model using these placeholders. Then you tell the framework to differentiate this, and it applies the symbolic differentiation rules, and it makes the graph transformation, gives you the derivative, and for taking care of the expression swell problem that I was talking about, it does some optimization step. And if you use Theano, this is the reason it's taking so long in the compilation step to get the derivative out. So you end up with the derivative graph as a result of the transformation, and you use that for getting your gradients so that you can use them in gradient-based optimization. And the problem with this is that you have severely limited and unintuitive ways of implementing things like branching and loops. You are supposed to use strange constructs for doing something like that. For example, if you use Theano, there is this thing called the scan operation. This is how you implement the loop, and they have rules of handling loops. So Theano is, for those who know, is implemented in Python. You are not allowed to use the for loop structure in Python, for example. It's completely out of the question. This is what I'm. Let me clarify what I mean by this. So for example, let's say you want to compute this a to the power of k. As a programmer, you will just, for example, write something like this, like multiply a k times with itself, right? So in TNO or TensorFlow, you cannot do this. You are supposed to use this very strange, unintuitive thing so that you can emulate doing some sort of loop like that. And this is happening because they are not using real automatic differentiation. This is happening because of symbolic differentiation. This is also the case for TensorFlow, also the thing that CNTK, Microsoft cognitive framework. So the difference in dynamic graph builders is that you have full support for control flow, branching, loops, recursion, procedure calls, whatever you want. So this is because if you remember this execution trace, what we are doing here is that we are just overloading operations that are supported by your language. Like if you just overload mathematical operations that and introduce derivative rules for them, you don't care about what the rest of your algorithmic control flow. You are blind to that. Look, this operation can be the result of an if statement. You don't care about that because it doesn't show up here. Or you could be in a loop. You could do these things many times. At the end of the day, any algorithm that you could write will be executed as a forward evaluation trace of mathematical functions. For getting a mathematical value, you will only do mathematical operations. So this is the reason why in, for example, PyTorch, you can just write this. Like this is sufficiently similar to the way you would do it in regular Python. You just define a PyTorch variable with the value initialized as 1. You just do your regular for loop, and you can get the derivative out. So we will look at that in the exercise session just to familiarize you with this. So this is something that is a recent development in the machine learning community. It started with Autograd, which is a project I think by now 2 or 3 years old right now. It was like a little Python project implemented at Harvard. Then the same people implemented that on top of the Torch deep learning framework, introduced automatic differentiation, general purpose reverse mode automatic differentiation to that. PyTorch came out of this lineage. It is a re-implementation of the whole Torch framework, just taking into account this automatic differentiation idea. This is a very important development, and I expect the other deep learning frameworks to follow this. So this is the reason I'm talking about it so much. Yeah, we will cover this in the exercise session. And the summary of all this is deep learning is neural networks plus data plus gradient descent. You do that for a long time. Sometimes you do like a week of training on a GPU just to teach a neural net to recognize some set of images. And you need a lot of data. So Tuanan is going to cover how this couples with probabilistic programming. So instead of having a training data set, you will get things from a probabilistic program where you also have labels, and if your model is good enough, you will get data that is sufficiently similar to things in nature or things in the problem domain that you are trying to address. And general purpose AD is something that is currently being adopted in the machine learning community. And so I expect more things to happen in this area because all this explanation I had about automatic differentiation was referring to operator overloading. There are other ways of doing these things. For example, you can do source-to-source transformations. This is not something even taught about in the machine learning community right now. You can do source transformation, automatic differentiation, which is something people do in computational fluid dynamics all the time. This is something that is waiting to be recognized by the machine learning community. There is no forward AD in any of these mainstream frameworks. You might think that it is not needed for machine learning, but if you have that, and if you have general purpose AD with nesting possibility, you can do things like you can do forward automatic differentiation, and you can apply reverse automatic differentiation on top of that, or you can do the other way, you can do reverse on forward. You can do many levels of differentiation to get things like higher order derivatives or Hessian vector products or any number of things that you can, you can have exact higher order derivatives that are useful for better optimization algorithms or implementing things like invariance in your neural network by just trying to minimize the derivative with respect to your network inputs, whatever. So if you have these things in your machine learning framework, it gives you more expressiveness to implement better machine learning models. So I guess that's the end of this. Actually, it's good because we are back on time. It's 11 right now. So I can take questions, and so we will do these things in the exercise session later in the afternoon. Yeah.
Thank you. I have a question. Maybe I missed it during the talk. So the deep learning frameworks, they estimate the derivatives analytically. So they use this. So they don't approximate them using finite elements, but they have this.
Yeah. Yeah.
And they don't approximate it using finite elements because of the error?
I think mostly because of the performance problem, because the main thing you need is a gradient. If you have a gradient, like if you have a function that is a function of 10 inputs, for finite differences, you have to do 10 evaluations of that. In each evaluation, you would add like this perturbation, this h, division by h. You add the h to the input, you divide by h, you do one evaluation, then you do the next, you do the next. It's like it's a very bad thing to do in terms of performance. I think that's the main reason. Because interestingly, deep learning models, these deep neural networks, they are very resilient with respect to errors. There are cases where people had a bug in their neural network that it was doing the wrong thing internally. It doesn't make sense mathematically, but it was still performing the task at the end of the day, because it learns to live with that and adapt the weights to function that way. So I think they wouldn't care about the approximation error too much if it was good enough performance, yes. Yeah. Oh, thanks. Okay. And they surpassed the previous state of the art. Another interesting application is machine translation. This is based on recurrent neural networks or convolutional neural networks. So again, this replaced the previous hand engineering features based statistical translation pipeline. And all major companies are deploying this as their daily machine translation system. The last was Facebook, which replaced their machine translation system just this month, a few weeks ago, with the full deep learning system. An interesting thing to see here is this plot for Google's neural machine translator. Here you see with blue the previous machine learning approach, non-deep learning. Yellow is the human. So you can see, for example, for the language pair, like translation from French to English, you get near human level translation performance, the quality of translation. And this is all happening just by supplying data to recurrent neural network. So I will try to cover why these things are starting to work so well, what makes deep learning tick, what is really the thing behind it. So probably all of you are familiar with artificial neural networks or the idea. So you have a mathematical structure very loosely based on a real neural cell. All right, so I'm a postdoctoral researcher in Frank's research group. We are working on probabilistic programming and applications in science, including high energy physics and high performance computing. I'm mostly interested in automatic differentiation, which will be the subject of this talk, and evolutionary algorithms and a bit of computational physics. So deep learning is one of the themes in this summer school, so I thought it would be good to provide an overview of that before going into the automatic differentiation part. So I don't know your level of familiarity with it, but let me just cover basic concepts in deep learning. So it is a reincarnation of artificial neural networks, which is a very old idea, and which was almost revolutionary. It halved the error that was achieved by non-deep learning techniques previously. You can see it happening here. This is basically the point where deep learning got to have the fame it has today, and it replaced hand-engineered features. And modern deep learning systems surpass human performance for image recognition tasks. This is also the case with speech recognition. Previously, people were using statistical methods based on hidden Markov models and Gaussian mixture models. Again, deep learning systems starting around 2012, they applied neural networks trained with lots of data, dating back to 1940s and 50s. Here you see Frank Rosenblatt, the inventor of the perceptron, which was, by the way, a machine instead of an algorithm, holding a set of neural network weights, which were like potentiometers that you can adjust by turning them and trying to teach the network to some task. And we use backpropagation, which was invented in 1970s. So all these things are very established old techniques that are currently working very well due to the things I'm going to summarize. So it is currently the state of the art in computer vision. This has been the case since this ImageNet competition in 2012, when someone attempted to apply convolutional neural nets for image recognition.